Look at this limit, and look at modulo 1 notation. It looks nonsense, but it's not. The definition of modulo 1 is different from what we usually see in modular arithmetic. It is the fractional part of a number, the difference between the number and its floor. For example, 3.7 modulo 1 is 0.7. Now look inside the root. If we complete the square, we get n plus 3 squared plus 6. For massive values of n, that root is basically just n plus 3. If n plus 3 is a whole number, its value modulo 1 is 0. That's why it looks like this whole term should just vanish. So we're left with infinity times 0. This is an indeterminate form. We need to calculate the exact rate at which that term approaches 0. To find this floor, we need to trap our expression between two consecutive perfect squares. Let's try n plus 3 squared. Expanding it gives us n squared plus 6n plus 9. Since 15 is greater than 9, our expression is clearly larger than n plus 3 squared. What about n plus 4 squared? That expands to n squared plus 8n plus 16. Since n is positive, 8n plus 16 is clearly larger than 6n plus 15. Our expression is now trapped between two consecutive perfect squares. Taking the square root, we see the value falls between n plus 3 and n plus 4. Since it's between two consecutive integers, the floor is simply n plus 3. Most people see infinity times 0 and assume the result is 0. That is a common error. To resolve this, we multiply by the conjugate, a standard tool for clearing radicals. The numerator becomes a difference of squares. This simplifies the expression significantly. When we expand, the quadratic and linear terms are identical in both parts. The n squared and 6n terms cancel out perfectly, leaving us with a simple constant. We are left with exactly 6n. The indeterminate form has been resolved. This is the final calculation. We have completed the algebraic work, and now we evaluate the limit. Standard play, divide every term by n. Just remember that inside the root, n becomes n squared. This simplifies the terms. Now we can identify the terms that approach 0 as n goes to infinity. At infinity, any term with n in the denominator approaches 0. These terms no longer affect the value. We're left with 6 over 1 plus 1. That's 3. Clean and simple. The algebraic manipulation was the primary task. The limit evaluation is the final verification.